Hey everyone, welcome to this deep dive.
Oh, yeah.
Where we're going to be looking at something you might not think about every day.
Right.
The connection between memory safety in programming languages
Yeah.
and the security of your data
Yeah.
and your devices.
Uh,
We've got a whole bunch of research here.
okay.
A document all about memory safety,
All right.
its role in cybersecurity, the good, the bad, and the ugly of programming languages when it comes to keeping information safe.
Yeah.
Our mission today
Okay.
is to help you understand how vulnerable your data, your devices might be based on the languages used to build the software that we all rely on every single day.
Absolutely.
By the end, I think you're going to be armed with some insights to make more informed decisions about the tech you use and maybe even, you know, impress your techie friends at your next dinner party or whatever.
Yeah.
Did you know that there are programming languages out there where certain types of devastating attacks are virtually impossible?
Oh, that's interesting.
Or that like a single coding error
Yeah.
can lead to like global ransomware mayhem?
Oh, yeah. No kidding.
So let's break it down, starting with the basics.
Yeah.
What is memory safety?
So think about it like this.
Okay.
Your computer's memory is like a massive city.
Okay.
And each program
Right.
that's running
Yeah.
needs its own building
Uh-huh.
to operate.
Makes sense.
It's allocated space.
Uh-huh.
So memory safety
Yeah.
is like having a super strict zoning board
Okay.
that makes sure that no program
Yeah.
can encroach on another's territory.
So it's like those high-rise apartments where everyone has their designated floor
Yeah, yeah.
and no one's like bursting into someone else's unit.
Exactly. In more technical terms,
Okay.
memory safety ensures that programs only access the memory locations that they're authorized to,
Uh-huh.
right? So that prevents accidental or even malicious interactions.
Nice. So like giving them a key card
Yeah, like a key.
that only works for their designated building.
Exactly.
Yeah.
Two key concepts here
Okay.
are bounds checking
Okay.
and type safety.
All right.
So bounds checking basically makes sure that programs don't try to access memory outside their allocated space.
So like they can't go
To another floor on
to a different building.
Yeah, okay.
And type safety basically makes sure that the data is used in a way that's consistent with its intended purpose.
Okay. So what happens when
Yeah.
a language doesn't have these safeguards in place?
That's when things get interesting
Okay.
and potentially dangerous. Okay.
Languages like C and C++,
Yeah.
while they're powerful and widely used,
Yeah.
don't have these built-in safeguards. They're kind of like cities with lax building codes where anyone can potentially build anything anywhere.
So it's like constructing a skyscraper right on top of a subway tunnel?
Yeah, basically.
That sounds like a recipe for disaster.
Yeah.
Can you give me an example
There you
of
go.
a real-world consequence
Yeah.
of using one of these memory unsafe languages?
Remember the heartbleed bug?
Yeah, that does ring a bell.
That was a classic example of what can go wrong
Okay.
with memory unsafe languages.
Okay.
It stemmed from a simple coding error.
Really?
Yeah.
Just a simple coding error.
It's called a buffer overread,
Okay.
and it was in a widely used piece of software
Right.
called OpenSSL.
Refresh my memory.
Sure.
What was so bad about Heartblade?
So think of it like this.
Okay.
A
Sure.
buffer is like a container
Okay.
for data
All right.
in a program.
Okay.
And a buffer overread is like trying to take more items out of the container than it holds.
Okay, so like you're reaching into a cookie jar and there are no cookies left.
Yeah, and your hand
But your hand keeps going.
keeps going.
Yeah.
And so it can cause the program
Yeah.
to read data from adjacent memory,
Oh.
which could contain sensitive information.
Oh, so
Like in the case of Heartbleed,
yeah.
this allowed attackers to potentially steal passwords,
Oh, wow.
encryption keys,
Hmm.
other sensitive data from servers all over the internet.
So one tiny coding error
Yeah.
could expose millions of people's data.
Potentially, yeah.
Wow, that's a sobering thought.
Yeah.
I'm guessing there are other types of vulnerabilities
Oh, absolutely.
besides buffer overflows.
There's a whole rogues gallery of memory-related vulnerabilities that keep security professionals up at night.
A bet.
We'll dive into those
Okay.
in just a bit.
Okay.
But for now, let's
Yeah.
focus on the other side of the coin.
All right.
The languages
Yeah.
that are designed with memory safety
Okay.
as a top priority.
All right.
These are like cities
Okay.
with super strict zoning boards,
Okay.
building codes enforced by robots,
Nice.
and 247 security patrols.
Oh, that sounds reassuring.
Yeah.
Can you give me a sneak peek at some of these memory-safe superstars?
One language that's gaining a lot of traction is Rust.
Rust. Okay.
It's known for its strict compiler, which acts like a super meticulous building inspector that catches even the smallest deviations from the memory safety rules.
Okay.
One of the key concepts in Rust is ownership.
Ownership. Okay.
Each piece of data in a Rust program has a single, clearly defined owner. And the compiler enforces strict rules about how that data can be accessed and modified.
So it's like each building in the memory city has a designated owner.
Exactly.
Who's responsible for keeping everything in order and making sure no one's like sneaking in through the back door.
Yeah, yeah.
Okay.
What other memory-safe languages are there?
Another popular choice is Go.
Go.
Or Golang, as it's sometimes called.
Got it.
It was developed by Google.
Okay.
It's known for its simplicity, its speed, and its built-in concurrency features.
Concurrency. Now, remind me what concurrency is again.
Yeah. So that enables it to handle multiple tasks simultaneously without getting tripped up.
So that's like our memory city, having multiple transportation systems running smoothly at the same time.
Yeah.
Like buses, trains, subways, without any collisions or delays.
Yeah, that's a great way to visualize it.
Yeah.
This makes Go ideal for building large, complex systems that need to be both fast and reliable.
All right, so we've got Rust, the strict city planner, and Go, the master of multitasking transportation.
Yeah, that's good.
What other languages?
Well, there's Swift, developed by Apple.
Okay.
It's primarily used for building iOS and macOS applications.
Okay.
You can think of Swift as Apple's own dedicated security force, ensuring that your iPhone data is protected from memory-based attacks.
Okay, that's good to know.
Yeah.
Now, I've also heard of Kotlin.
Yes.
What's special about that one?
Kotlin is a great option for Android app development. One of its standout features is something called null safety.
Null safety.
Yeah, and it's designed to prevent
a whole category of errors that can crash apps or even entire systems.
Wow.
Think of it as making sure that every building in our memory city has a solid foundation.
Okay.
So there's no risk of it suddenly collapsing.
So Rust, Go, Swift, Kotlin.
Yeah.
Those are the ones to look for.
They're definitely some of the top contenders.
Yeah.
But there are a few more worth mentioning, like Haskell, Ada, Java, and C#.
All right, so
these languages all have their own strengths and are widely used in various areas where security is paramount.
This is all fascinating stuff.
There it is.
It's really amazing to see how these different programming languages are like different cities, each with their own unique layout, infrastructure, security measures.
Yeah, that's a great way to think about it.
Yeah.
But let's not forget that choosing a memory-safe language is only part of the equation.
Oh, okay.
The developers who build the software also play a crucial role.
Makes sense.
In ensuring its security.
Okay, so it's a team effort.
Yeah.
We need well-designed languages. Skilled developers and informed users to create a truly secure digital environment.
That's a great way to put it.
Yeah.
And speaking of informed users,
yes,
let's move on to explore the darker side of memory safety. The actual attack techniques that exploit these vulnerabilities.
All right.
Hold on to your hats, folks.
Okay, I'm ready.
Because we're about to enter
the
world of cybersecurity nightmares.
Oh, I'm both intrigued and a little bit terrified.
Yeah.
Okay, lead the way.
Let's do it. Welcome back to our deep dive into the world of memory safety.
Before we went to break, we were talking about memory-safe languages, like meticulously planned cities. But how does choosing one programming language over another actually affect my day-to-day online security? I mean, it's not like I'm coding these apps myself.
That's a great question.
Yeah.
It all comes down to the foundations of the software you use every day.
Okay.
Your web browser. Your banking app. Your smart home devices. They're all built using code written in some language.
Makes sense.
And if that language is prone to memory vulnerabilities, it's like building a house on a shaky foundation.
So even if the developers try to be super careful, if the language itself has weaknesses, the whole app could be at risk.
Right.
It's like even if you have the best contractors, a house built on a fault line is still vulnerable to earthquakes.
That's a great analogy.
Yeah.
And unfortunately, you can't always tell just by looking at an app what language it's built with.
Okay.
But the more aware you are of this issue, the better equipped you'll be to make informed decisions.
So what should we be doing?
Well, maybe do a little digging online. Before you download that new app everyone's raving about. See if you can find out what language it's built with. Read some reviews from tech-savvy users who might mention security aspects.
So it's kind of like checking the nutrition label on food before you buy it. We should be doing the same for software.
Exactly. Now, let's talk about the real threats. We've hinted at the dangers of memory unsafe languages. But let's explore what those attacks actually look like. Think of it as understanding the tactics of those who might try to exploit these weaknesses.
I'm ready to face my cybersecurity fears head on. Let's do it.
Let's revisit the infamous buffer overflow, the granddaddy of memory-based exploits. Remember our container analogy? A buffer is like a storage container for data. In a program, a buffer overflow happens when someone tries to stuff more data into that container data can hold.
Like cramming a whole wardrobe into a suitcase. Something's bound to burst. But how does an attacker actually cause a buffer overflow?
So it's more targeted than you might think. Hackers often carefully craft their input, like a malicious message or a rigged file, to trigger the overflow.
So they're not just throwing spaghetti at the wall and seeing what sticks.
It's very strategic.
They actually plan these attacks.
Exactly.
Wow.
They exploit weaknesses in a program's code to inject their own malicious code, like a virus. Once they've caused a buffer overflow, they can potentially gain control of the affected system.
So it's kind of like finding a back door.
Yeah, like a back door.
Into a building that lets them bypass security.
Exactly.
Okay.
That's pretty unsettling.
Yeah. What kind of damage can they do once they've triggered a buffer overflow?
It can range from something as annoying as a system crash to something as serious as stealing sensitive data. Or even taking over entire networks.
Wow.
Remember, even a single coding error can have ripple effects.
Speaking of ripple effects, let's move on to another type of attack. What about those use-after-free vulnerabilities we talked about earlier? The image of trying to get into a demolished apartment is still stuck in my head.
It's a good one to remember. Because it highlights the core issue. These vulnerabilities happen when a program tries to access a memory location that's already been freed up. Like trying to use a key to a room that's been torn down.
Makes sense.
An attacker can exploit this to sneak their own malicious code into that empty space.
So it's like the digital equivalent of booby trapping an abandoned building. Yikes.
What makes these use-after-free attacks so tricky?
Why are they so hard to stop?
They're often hard to detect. Because they involve subtle timing issues within the code. It's like trying to catch a thief who only strikes when the security cameras blink.
Wow.
It's all about exploiting those tiny windows of opportunity.
Let's talk about another vulnerability, dangling pointers. It sounds like something out of a horror movie.
It can be pretty scary in the cybersecurity world. Think of a pointer as like a digital signpost that points to a specific location in memory. A dangling pointer is like a signpost that's still pointing to a building that's been moved or demolished.
So the program is following a sign that leads to nowhere. Or worse, a dangerous place.
Or worse.
Set up by an attacker. And just like with use-after-free attacks, dangling pointers can allow attackers to gain unauthorized access to memory or even inject their own malicious code. Okay, I'm starting to understand the pattern here. These memory vulnerabilities are all about exploiting confusion and misdirection Within a program's code.
Exactly. Okay. Let's talk about something called an integer overflow.
Integer overflow. Okay.
Now, integers are just numbers.
Right.
But they can cause big problems.
Right.
When they exceed their limits. Think of it like a car's odometer rolling over back to 0.
Okay.
After reaching its maximum mileage.
Yeah. So it's not that the numbers themselves are dangerous.
Yeah.
But what happens when they overflow their intended boundaries?
Exactly.
Like a glass of water overflowing when you pour too much in.
That's a good way to visualize it.
Yeah.
An integer overflow can cause a program to behave unpredictably. Potentially leading to crashes, memory corruption, or security holes.
It's amazing how something as seemingly simple as a number can be weaponized in a cyber attack.
It's true.
What else?
Next up are format string vulnerabilities.
Format string vulnerabilities. Okay.
These are a bit more technical.
Okay.
But essentially they involve exploiting the way a program formats text output.
Okay.
Imagine a hacker manipulating the formatting codes in an email to inject hilly commands.
So it's like sneaking a secret message into the margins of a letter.
That's a good way to think about it.
Yeah.
If an attacker can control the format string, they can potentially access or modify sensitive data. Or even execute their own malicious code.
Wow.
It's like giving them the power
to
rewrite the rules of the game.
We're really getting into the weeds here.
We are.
But it's fascinating to see how many different ways these memory vulnerabilities can be exploited.
Yeah.
What's next?
Let's talk about race condition exploits.
Race condition exploits.
Yeah. These are tricky. Because they rely on exploiting the timing of events. Within a program. Imagine two people trying to withdraw money from the same bank account at the same time. If the timing is just right, one of them might be able to withdraw more money than they actually have.
So it's like a race between the attacker and the security measures?
Exactly.
And if the attacker wins, they get the prize.
They get the prize. In the context of cybersecurity. This could mean bypassing security checks, escalating privileges, or even causing a denial of service attack.
Okay, so we've covered buffer overflows.
We have.
Use after free attacks. Dangling pointers. Integer overflows. Format string vulnerabilities. And race conditions.
We have.
Are you trying to give me cybersecurity anxiety here?
Just 2 more to go.
Okay.
And then we'll move on.
Okay.
To some more positive aspects of cybersecurity.
Okay, good.
Next up are heap spraying.
Heap spraying?
And heap manipulation.
Heap spraying, that sounds like something you do to get rid of weeds in your garden?
Yeah.
What does it have to do with cyber attacks?
It's not nearly as benign as gardening, I'm afraid.
Okay.
The heap is a portion of memory used for dynamic allocation. And heap spraying involves flooding it. With malicious code. Making it more likely that the program will accidentally execute it.
So it's like hiding a needle in a haystack.
Yeah.
But the haystack is the computer's memory.
Exactly.
And the needle is the malicious code.
That's a good way to visualize it.
Yeah.
And heap manipulation techniques can be used to exploit other vulnerabilities, making them even more dangerous.
Okay, last but not least.
All right.
What's our final memory menacing attack type?
We'll wrap up with memory leak exploits.
Memory leak exploits.
Yeah.
These might not sound as dramatic as some of the others.
Yeah.
But they can be just as disruptive.
They can be.
Memory leaks, is that like when my brain forgets where I put my keys?
It's a bit like that.
Okay.
But with more serious consequences.
All right.
A memory leak occurs when a program doesn't release memory. That's no longer needed. Like holding onto old files you never use until your hard drive is full.
So it's not a direct attack,
right?
But more of a way to bog down the system and make it vulnerable.
Exactly.
Like slowly filling a room with junk until there's no space left.
That's a great way to think about it.
Yeah.
Attackers can deliberately trigger memory leaks to exhaust a system's resources, causing it to slow down, crash, or even become unresponsive.
So it's a denial of service attack.
Yeah, it's a denial of service attack.
By a different name.
By a different name.
Wow, we've really gone through the gauntlet of memory-based attacks here.
We have.
I'm feeling a bit overwhelmed.
I understand.
By all the potential threats lurking in the digital shadows.
It can be daunting.
Yeah.
Delve into the darker side of cybersecurity.
Yeah.
But remember, awareness is the first step to protection. Now that we've explored potential dangers, let's shift our focus to the more positive side of things.
I'm ready for some good news. What are some proactive steps that users and developers can take to make the digital world a safer place? Welcome back to the deep dive. We've explored the importance of memory safety in programming languages, and we took a pretty deep dive into that dark world of cyber attacks that exploit those weaknesses.
Absolutely.
Now let's talk about what we can do to protect ourselves and build a more secure digital world.
I agree. I think the good news is that knowledge is power. And the more you understand about these vulnerabilities, the better equipped you'll be to make informed decisions.
Exactly. So what can we do as everyday users?
So one of the most important things is to be mindful of the software you choose. As we discussed, the programming language that an app is built with can have a big impact on its security. You might not always know what language an app uses just by looking at it.
So like checking the ingredients list on a food product. Read
reviews from other users. Check out the app developer's website. See if they have a section on security. You might even consider reaching out to them directly with any questions you have.
So being an informed consumer is key.
Absolutely.
What else can we do?
Keep your software up to date. Those annoying update notifications. They're often delivering critical security patches that address known vulnerabilities.
So it's like upgrading the locks on your doors and windows.
Okay,
no more ignoring those update reminders.
Yeah.
What about when we're browsing the web?
Be wary of links from unknown sources. Avoid websites that look suspicious. You can even consider using a privacy-focused browser that has built-in security features.
So be street smart in the digital world. Don't wander into dark alleys. And don't click on shady links.
Don't click on shady links. Use strong, unique passwords and enable two-factor authentication.
So we've got the user side of things covered. What about the developers?
There's a lot of great work being done in the developer community. One positive trend is the increasing adoption of memory-safe languages. Like Rust, Go, Swift, and Kotlin.
So they're building those memory cities with the strict zoning boards and the robot building inspectors. In addition to choosing safer languages, developers are adopting more rigorous testing practices. They're collaborating with security researchers. So like a multi-pronged approach to making things safer. Is there anything else that can be done?
That's a great question. There's a growing discussion about the potential for regulations or industry standards to encourage the use of memory-safe languages.
That makes sense.
Especially for software that impacts a lot of people or handles sensitive data.
But that seems like it would be hard to implement.
It definitely wouldn't be easy. But the fact that we're having this conversation is a positive sign. It shows that memory safety is being recognized as a critical aspect of cybersecurity.
We've come a long way in this deep dive.
We have.
We started by talking about the nuts and bolts of computer memory. And now we're talking about
I know, it's great.
Potential regulations and the future of software.
That's what I love about deep dives. We uncover these connections and implications that go way beyond our initial focus.
As we wrap up, what's the one key takeaway?
I hope listeners come away with a better understanding of how the choice of programming language can impact software security. And how that, in turn, affects their own digital lives.
Makes sense.
Memory safety is not just a technical detail. It has real-world consequences.
Absolutely. So let's all be mindful of the software that we use, support developers who prioritize security, and continue to learn and stay informed about cybersecurity. It's an ever-evolving world.
It is.
Let's not take our digital security for granted.
No.
Thanks for joining us on this deep dive.
Thanks for having me.
Into the fascinating world of memory safety and cybersecurity.
It was fun.
Until next time.
Yeah.
Stay curious, stay informed.
Yeah.
And stay safe out there.